Good day, everyone. Allow me to introduce myself. My name is Alsharizani Putra, and today our group from machine learning class would like to talk about naive Bayes method. And as for today, beside of myself, I have my friend Arya Radzika Pradayan and Haris Hamzah Hutapea, who will be explaining about naive Bayes method in the upcoming slides.
So, what is naive Bayes? Naive Bayes is a supervised learning algorithm primarily designed for classification tasks, making it one of the simple yet powerful tools in machine learning. It is based on the Bayes theorem, a foundational concept in probability theory that describes on how to update probability of a hypothesis as evidence becomes more available. The key idea behind naive Bayes is to use this theorem to calculate the likelihood of different classes for a given set of features and then predict the class with the highest probability. Despite its naive name assumption that all the features are independent of each other. Given the class label, naive Bayes can perform remarkably well in many real-world applications. This independence assumption implies that the presence or absence of one of features that does not influence the others. While this is an oversimplification in complex dataset, it allows the model to make fast and efficient prediction. Naive Bayes is particularly well suited for problems such as text classification, spam detection, and sentiment analysis, where features such as word counts are treated independently. The model to handle both a small and large data set and its minimal computational requirement and its effectiveness with both discrete and continuous data make it a popular choice for many practical applications. So the theoretical ideas of naive Bayes. So the first we have to talk about the Bayes theorem. So let's break it down. We because the Bayes theorem is a core foundation of naive Bayes. This theorem is fundamental concept in probability theory that allows us to update the probability hypothesis as new evidence becomes available. Essentially, it's about revising our prior belief in light of new data. In context of naive Bayes, it helps us calculate a particular class given the observed features. So the Bayes theorem is expressed as PC x1 x2 to xn equals to PC times P uh, in the bracket x1 x2 till xn and then C divided by P x1 x2 to the xn. So basically, the result is the posterior probability, the probability of class C after considering evidence features like x1, x2, or xn. And then the PC is a prior probability class of C, representing our initial belief before observing any evidence. And then P x1, x2 is the likelihood, so the probability of observing the features given the class. And then the last P x1 to xn is the evidence, the overall probability of observing the given features irrespective to the class. So why is it important that we know the Bayes theorem before we do naive Bayes? It is because the Bayes theorem allows us to invert conditional probabilities, essentially recalculating the probability of a hypothesis given the new observation. This inversion is particularly useful in situations where direct computation is challenging, but the likelihood is easier to determine. So the thing is that Bayes theorem is like updating your weather prediction based on new information. Suppose your initial forecast is 50%, and then when you saw the sky is a bit cloudy, and then you could uh, up the likelihood. So that's basically the simplified of Bayes theorem. So the second is assumption of conditional independence. So the knife bias classifier operates under a key assumption called conditional independence. This assumption is at core of knife bias simplicity and efficiency. It means that the given class label, the probability of one of the feature is treated as an independent of the probability of other features. In other words, the presence or absence of features does not affect the presence or absence of another feature when the class label is known. So, what does the conditional independence mean? So, in real world scenario, this assumption implies that the features are considered unrelated when they are observed together. For example, if we classify emails as spam or not spam, knife bias treats the presence words like free, discount, winner as independently contributing to the likelihood of the email being a spam, even though these words often appear together in actual spam emails. So, and then the formula representation is that pxn y equals to px 1 y times px2 y to the pxn y. So basically, here each feature xn is conditionally independent of the others, given the class y. This allows the model to compute probabilities by multiplying likelihood of each feature independently. So the third one is classification mechanism. So knife bias works by calculating the posterior probability for each class, given the observed features, and then assign the instance of the class with the highest probability. This makes it efficient and straightforward algorithm for classification tasks, especially when dealing with multiple classes. So let's break down the classification mechanism. So knife bias uses bias theorem to estimate the probability of an instance belonging to each class given its features. The class with the highest probability is selected as the predicted class. So the for as you can see the formula for classification. So the posterior probability for each class CK is calculated as you can see in the screen. I'm just going to explain it. So the first part is the PCK XN. So it's the posterior probability of the class CK given its features, and the PCK is the prior probability of class CK, and then the last one is the PXICK. It is the likelihood of observing features X given the class CK. So the product term represents the combined likelihood of all features of CK. So how knife bias classifies new instances? So it is classify new instances by first by prior probabilities, likelihood, posterior probability, and class assignment. So there is also decision boundaries. So decision boundary in knife bias often creates a linear decision boundaries, which means it separates classes using straight lines or planes in higher dimension. In a 2D feature space, this probably translates to a line dividing the classes. For instance, in text classifications, the decision boundary might be a line that separates words likely associated with spam or those associated with non-spam. So while linear boundaries is arise because the model uses the product of likelihoods, which resulted in linear separation between classes when plotted. This simplification is what makes knife bias fast and effective, since especially for the problems where the classes are linearly separable. So the last one I'm going to discuss is types of knife bias classifiers. So knife bias has several variants, each tailored to handle different types of data or distribution. By adapting these various types of data types, these classifier can be used effectively across a wide range of application. So the first one is Gaussian knife bias. So Gaussian knife bias is specifically designed for continuous variables and assumes that these variables follow a Gaussian or a normal distribution. It's particularly useful when working with features that have continuous numeric values such as age, height, or temperature. So, and then when to use Gaussian knife bias? So it is best suited for continuous features that are normal distributed. For example, predicting a person's weight based on their height and age, where both features are continuous and approximately normally distributed. So the second one is multinomial knife bias. So multinomial knife bias is designed for discrete data that can be represented as counts or frequencies, making it ideal for text classification where features represent more counts. So it has some characteristics such as it particularly useful for features that represent the number of times that discrete event occurs. It models the features as distribution as multinomial, considering the frequency of each features in the training data. So when to use this multinomial knife bias? So it is, well, just like I said, it is best to use for discrete data, especially when features such as counts or frequency. So, for example, the word counts in a text document where each feature represents the number of times that a specific word has appeared. So the last one is the Bernoulli knife bias. So but the Bernoulli knife bias is designed for Boolean or binary features, where the features represent binary outcomes such as 0 or 1. So it is best suited for tasks where the features indicate presence or absence of certain attributes. So it has some characteristics. So it models the features as Bernoulli distributed variables, meaning each feature is treated as either present 1 or absent 0. Unlike multinomial knife bias, which consider the frequency of features, the Bernoulli knife bias only consider whether the feature is present or not. So, when to use Bernoulli knife bias? So, best is for binary data, as I mentioned. So, for example, the presence or absence of certain words in an email. IG, for example, whether the word win or the word free appears or not. So, uh, basically, in choosing the right knife bias variant, so if your features are continuous and resemble a normal distribution, use Gaussian knife bias. But if your features are discrete counts of or frequency like word count, use multi-nominal knife bias. But if your features are binary or represent presence or absence of characteristic, use Bernoulli knife bias.
Next up is how knife base work. Knife base work divided into two: the training phase and prediction phase. The training phase, the algorithm learns prior probabilities for each class as well as the likelihoods for each feature given the class. These probability are typically estimated using the relative frequencies in the training data. In the predicting phase, for a new instance with known feature values, the classifier calculates the posterior pass-up probabilities for each class and selects the class with the highest posterior probability as the predicted class. Next up is how naive Bayes work. Naive Bayes work divided into two: the training phase and prediction phase. The training phase, the algorithm learns prior probabilities for each class as well as the likelihoods for each feature given the class. These probability are typically estimated using the relative frequencies in the training data. In the predicting phase, for a new instance with known feature values, the classifier calculates the posterior pass-up probabilities for each class and selects the class with the highest posterior probability as the predicted class. An example of naive Bayes in real-world application. The first one is Gaussian naive Bayes for continuous data. The example application is iris forward classification. The dataset is the iris dataset, which contains continuous numerical features such as petal and sepal length and width. The goal is to classify iris flowers into one tree species, Setosa, Veriscolor, Virginica. Why Gaussian? The features are continuous, and Gaussian naive Bayes assume that the likelihood of the feature follows a Gaussian normal distribution. The second example is multinomial naive Bayes for discrete data. Example application, text classification, for example, spam detection, dataset, a dataset of emails or documents where the feature represent the frequency of specific words. The goal is to classify emails as a spam or not a spam based on the word occurrence. While multinomial, the feature represent word counts or frequencies, which are discrete values, making multinomial naive Bayes ideal for this task.
Now, another example of knife bias in real-world application is Bernoulli knife bias, or the use of it for binary data. An example of application is sentiment analysis. Basically, a data set of movie review where features indicate whether certain words are present or absent in each review. So, what is the goal? The goal is to classify reviews as a positive or negative based on the presence of specific words. Why Bernoulli? The features are binary, indicating whether a word appears one or not, which fits the knife bias model. Based on all of our explanation of the knife bias method, here is the summary of advantages and disadvantages that we found for the knife bias method during our research. For the positive, knife bias method is quite simple and fast. It also handles high dimensional data very well. It performs well with small data sets and works well with categorical input data. It also has multi-class classification and robust to irrelevant features. Now, for the negative is that knife-based method tend to some strongly of feature independence. It has zero probability issue and it is very much sensitive to imbalanced data. It is not very suitable for continuous data without a Gaussian assumption and cannot capture feature interactions. And it really relies on conditional independence. So, in conclusion, after all of our explanation, knife bias offers a balance between simplicity and efficiency, particularly useful for tasks like text classification. Its limitation in real-world applications stems from the independence assumption, but methods like Laplace smoothing can mitigate some of the challenges that is found in the knife bias method. This is the end of our knife-based method presentation. We would like to say thank you very much, and we would also like to say sorry if there is any wrong saying in our presentation. And thank you.